So the last talk of this session is given by Noam Touitou. Please.
Hi, I'm Noam, and I'm going to talk about an algorithmic framework for metric optimization problems with deadlines or with delay. And this is joint work with Yossi Azar. So the structure of sort of a normal online problem is something like this. You have a space of possible requests, and we are going to focus on the case in which that space is a metric space. Then an adversary requests some point in that space of requests, and then the algorithm responds by performing some action which serves that request. And that action incurs some cost. Then the adversary requests another point, the algorithm responds again, and so on. And the goal of a solution is to have minimal cost, which is the minimal cost of responding to all of those requests in whichever problem you're considering. Now, you can think about the case, you can think about the fact that if this model is in fact quite restrictive in that it only allows for the serving of a single request at each point in time. Now, you can imagine problems in which if you, for example, had like 4 requests coexisting in the same time, you could serve all of them, and that would cost you much less than serving each of those 4 requests individually. So this is the motivation behind the deadline model. So in problems with deadlines, now the requests arrive over a timeline. And each request, when it arrives with an associated deadline. So now you can see Q1 has arrived on some point in the metric space. And after some time, Q2 arrived on another point. And now at some point in time, a solution might serve both of those requests together, which is potentially cheaper than serving them apart. Now, there's another mechanism with the same purpose, which is more general, and that is the mechanism of delay. So in online problems with delay, the requests again arrive over a timeline. But now, instead of having an associated deadline, they have an associated delay function, which is monotone non-decreasing. So what happens now is that the algorithm is motivated to serve the request earlier, because at the moment in which the request is served by the algorithm pays the value of the delay function at that time. So the earlier, the better. Now, this can only, so the new cost function here is the original cost function of the problem plus the total delay cost over all the requests. And you can, in fact, see that delay is, the deadlines are a special case of delay because you can approximate the deadline using a delay function which looks like a step function. Okay, so it's supposed to be something like 0 until the deadline, then infinity after the deadline. Now, this is just general talk about deadlines and delay. And in this talk, I'm going to focus on 3 problems. So the first problem is the multi-level aggregation problem, presented here with deadlines. So in this case, the metric space on which requests are released is the leaves of a tree. And now the requests arrive on the leaves of the tree, and the deadline is listed next to the request. And now at some point in time, a request reaches its deadline, so the algorithm has to serve it. And the way the algorithm serves requests in this problem is by transmitting a subtree. So this happens here. So the algorithm transmits a subtree, and that subtree must contain the root of the tree. And each leaf that is touched by the subtree gets all the requests all the pending requests on that leaf served. So this is what happens here. So the 1, 3, and 6 requests are served, and the 4 request is not. And then, of course, after transmission, the transmitted subtree disappears. Now another request might arrive after that, and so on. The goal is to minimize the sum of total transmission costs over the tree. So the cost of transmitting a tree is the total weight of that tree. So here's the same problem with delay. So now you have, instead of deadlines, have associated delay functions. So here request A has its own function, request B has another function, and the algorithm transmits a tree serving both of those requests, paying the cost of the tree, as well as the values of the delay functions of both request A and request B. So this problem is quite general. It's usually considered with the parameter d, which is the depth of the tree. And now this problem was considered for constant d in various names. So if d equals 1, it's the TCP acknowledgement problem. If d equals 2, it's the joint replenishment problem. For both of those problems, there are constant competitive algorithms. And the first consideration of the multi-level aggregation problem for general trees was by Bienkowski et al. And they showed an algorithm which is exponential in the depth of the tree for multi-level aggregation with delay. So this is the more general one. And for the more specific model of deadlines, there was an improvement by Buchbinder et al. To O of d. Okay, so this is an exponential improvement, but this leaves an exponential gap between the deadline case and the delay case, which begs the question, can the delay case be improved similarly? The second problem is the problem of service with delay. So service with delay is what you get when you convert the K-server problem to a problem with delay functions. But in contrast to the K-server problem, this is interesting even in the case of a single server. So the problem is you have now a single server on a metric space, a general metric space, and you get requests on the points of that metric space. And in order to serve those requests, you have to move your server to the point of the request, paying the distance traveled by the server. So this was introduced by Azar et al. And they gave a log to the fourth n competitive algorithm, where n is the number of points in the metric space. And for some special metric spaces, there are better results, such as a constant competitive algorithm for the uniform metric or an O log n for the line metric. And the third problem we're going to consider, and this is the one I'm going to focus on in this talk, is the facility location problem with deadlines or with delay. So now you again have requests on a general metric space. But now the way to serve requests is by opening a facility at some point and connecting pending requests to that facility. And the cost of doing that is a cost of f for opening a facility plus the distances from the facility to the requests that are served. And a property of this problem is that the facilities are, in fact, temporary. So you open them, you connect the requests, and after you do that, the facility immediately disappears. Okay, and the goal is to minimize the total opening cost plus the connection cost. Okay, so opening cost, the cost of opening a facility, connection cost, the distances from the facility to the requests. So this is a problem we present in our paper. But there is a consideration of facility location in the online setting. This classic consideration features permanent facilities. Okay, so in that problem, once you open a facility, you get to keep it and use it to serve subsequent requests throughout the input. In our case, these are momentary facilities. So you open, you connect, then the facility disappears. So this is sort of renting a facility instead of buying it. This is the intuition for this. So to some of the results of those problems I've discussed, so for the multi-level aggregation case, there is an O of d competitive algorithm where d is the depth of the tree. And this is for deadlines. And for delay, there is only exponential in d. For service with delay, as well as service for deadlines as a special case, there is log to the fourth of the number of points in the metric space. For facility location, there are no results since we just introduced the problem. In our paper, we show a similar exponential improvement for multi-level aggregation with delay to O of d squared. And in fact, our algorithm, if restricted to problems with deadlines, would also produce the O of d, matching the best known upper bound. For service with delay, we give a log squared n competitive algorithm, which also applies, of course, to the deadline case. And for facility location, we give as well a log squared n. And those algorithms, they share the same general framework. And the way that the framework inspires the algorithm also inspires the analysis of that algorithm. And I'm going to focus on the problem of facility location with deadlines in this talk, since this most clearly illustrates the concepts of the framework. So we get to facility location with deadlines. And we're going to focus on the case in which the metric space is the leaves of a tree, which is more general than you might have thought, because we can embed a general metric space into a tree. Thus, this algorithm is in fact the heart of the algorithm for the general case. So now the requests are on the leaves of a tree. And the way to serve requests is by opening a facility at some point in the tree, which we also allow opening facilities on internal nodes, so not only on the leaves, even though they are the points of the metric space. So this is like a constant loss, so it's OK. And then you connect requests, then you close the facility, and that is the problem. So the way our algorithm works is, upon an expired deadline, a service is started by the algorithm. And the service opens a bunch of facilities and connects a bunch of requests to those facilities. And a property that it's going to have is that the facilities are upwards closed. So if a facility is opened in a service on some node, then a facility is also opened on its parent node. And the way we construct a service is by repeated explorations of nodes. So what happens in an exploration of a node? A facility is opened in that node, and that facility looks downwards on the pending requests in the subtree rooted at that node, and it serves some of them and performs some actions, which we're going to see. And each service starts with exploring the root node. So how does the algorithm work? So here you see the algorithm as well as its internal state. And the internal state consists of a counter of size f, which is near every node in the tree except for the root. And that counter starts off as empty. And now suppose a request reaches its deadline. So we start exploring the root node. And that exploration starts with opening a facility at the root node. And it is given a budget of f to spend. And let's see how it spends it. So it looks on the pending requests underneath it. So in this case, it's the entire tree. And it considers them by order of increasing deadline. So the first request it's going to consider is, of course, the request which has just reached its deadline. So it considers a request. And then it considers the distance between the request and the facility. And it tries to transfer an amount of budget which is equal to that distance to the child node in the direction of that request. So this is what it does here. So it transfers this amount from its budget to the counter. And now one of two things happens. So the first is that the counter of the child node is not full. In this case, the request is connected to the facility of the exploration, in our case, the root. And this is also what happens here. The second case in which the counter is full, we're going to see in a bit. So now it considers another request, transfers more budget. The counter is again not full, so the request is connected, and so on. And now it's out of budget. So the exploration is over, thus concluding the service. OK. The counters, by the way, are persistent throughout the run of the algorithm, so they remain also after the end of the service. And now time continues to flow, and some other request reaches its deadline, starting yet another service. So again, a facility is opened in the root, it gets its budget, and now it tries to transfer to the child node, but this time the counter of the child node is full. So instead of connecting the request to the facility, the exploration of the root node recursively calls an exploration of U2. So now a facility is opened in U2, U2 gets its own budget of F, and it spends it on connecting various requests. And once it's out of budget, the exploration of U2 is over, and control returns to the exploration of R. And R then spends its budget connecting more requests until it's over, thus concluding the service. So this is the structure of the algorithm. So it has this DFS-like structure of explorations used to construct a service. And this is what extends to the other problems we consider, which are the multi-level aggregation problem and the service with delay problem. So this is, in fact, the framework. OK, this is the algorithm in words. And the way to analyze this sort of algorithm, well, the overview is similar to any analysis of an online algorithm. You want to show competitiveness, so you upper bound the cost of the algorithm. You lower bound the cost of the optimal solution. Upper bounding the cost of the algorithm in this case is pretty simple, so I won't focus on that. But I will say something about lower bounding the cost of the optimal solution. So what is the way to do this in this case? So we're going to construct something called a preflow. So what the intuitive way to describe what a preflow is you build a set of containers and pipes between those containers. And you have this tap over there. And you open the tap for a bit. And then you close it. And then after you do that, the state of the system looks something like this. So there's water in various containers. And the property you can say about this thing, which I don't think requires any proof, is that if you choose any subset of containers, the amount of fluid in those containers is a lower bound for the amount of fluid that came out of the tap. And this is basically the argument behind this. However, we do need to build this set of containers and pipes and prove that, that we have some amount in our containers, and that also what comes out of the tap is the cost of the optimal solution. And once we do that, that yields the proof. And this is how our preflow looks like. So yeah, so to conclude, this framework, which I sort of talked about for the facility location with deadlines problem, also extends to the facility location with delay case and service with delay. And for all of those, gets log squared n competitive algorithm. And it also works for multi-level aggregation with delay, getting an algorithm which is d squared, where d is the depth of the tree. Yeah, and then again is the number of points in the metric space. OK, so for future directions, improving the upper bounds and getting lower bounds are both important. The main problem here is that there are no non-constant lower bounds. OK, so there is a gap between like constant in d and constant in log n that needs to be filled somehow, either with upper bounds or with lower bounds. And that is the most interesting problem in this sort of problems. Applying the framework to additional problems with deadlines or delay would be nice. But even more generally, this concept of using preflows in proofs is very, very, very general. Okay, so this has nothing to do with online algorithms. This is just a tool which proved to be very adaptive in general. And when we had problems writing the paper, we could always find a way to tweak the preflow to support solving this problem. So this is a very adaptive tool. I don't know how far it can go, and I would sure like to find out. Okay, so thank you.
Okay, do you have any question? Over there.
So when you say that like the algorithms that you have are randomized, are those because you have to embed these metrics embedding between?
Yeah, there is like an HST embedding going on from the general metric space to an HST. Well, sort of an HST, similar thing. So yeah, so the heart of the algorithm is on this tree. There is through some careful calculation, we in fact don't lose anything from doing this embedding, which is like a property we sort of got throughout the paper for some reason. The thing is the embedding sort of distorts the distances, but in our problems, it turns out that on the distances we're actually better off than on the opening cost of facilities, for example. So it turns out that this distortion does not affect the competitive ratio.
Other questions? I don't see any. So okay, thanks again.